Hello everyone, let us get started with the traditional high point culmination of our winter meetings, the great lecture in astronomy. At this point, of course, it is my pleasure to also welcome the general public joining us as part of the Texas Science Festival. It's also my pleasure to invite everyone who is joining us online via the YouTube connection. And of course, really everyone is very, very welcome to this really special event. So just by way of introduction, introducing our speaker, Professor Steve Finkelstein, faculty member in the Department of Astronomy at UT Austin. So Steve is fantastic, impressive, however you look at him. He joined us, the faculty, in 2012. Before that, he was a NASA Hubble Fellow, got his undergrad degree, University of Washington, then his PhD, Arizona State University, and so we are so very, very proud to have him. But let me also say that besides leading the James Webb Space Telescope, and before that Hubble Space Telescope and other observational programs at the very, very cutting edge, Steve plays important roles in many, many other fields. He is a very, very accomplished teacher with great distinction, has won a number of prestigious teaching awards, including the UT Provost Fellow Award. And in this capacity, Steve is bringing great innovation to his classroom. So he is really bringing new ideas of incorporating undergraduates early into cutting-edge research. So teaching, extremely impressive as well. And then also he is also serving as our department's associate chair, and it really was an incredible pleasure to interact with Steve in the chair's office, helping to guide our department. So in many, many ways, Steve is fantastic, and it gives me incredible pleasure now to cede the stage to Steve for our 2023 great lecture on the cutting-edge frontier discoveries with the James Webb Space Telescope, the JWST. Steve, please.
Thank you very much, Volker, for an amazing introduction. It's a great pleasure to be here in front of all of you, Board of Visitors members, everyone else, science enthusiasts here in the room and online for really the first time in so many years, talk about JWST and the amazing science in the present/past tense. We've been talking about this telescope in the future tense for so long. I almost put all the title slides of BOV talks I've given about this telescope, but I decided not to because it would clutter the slide. But I think I've given 6 talks about this telescope since I got here 11 or 12 years ago. So today I'm really excited to share with you what the telescope has done since launch. We're going to start with launch, spoiler for the next slide. And then we'll talk about the path to science. We'll talk a bit about how we actually do what I do, which is study galaxies in the early universe. And then I'll show you some of the amazing results. And I'll just sort of give you one of the summaries now, which is I really kind of failed to imagine not only how well this telescope would work, but what the universe actually had in store. And so some of the results we'll see, I never imagined I could be so surprised by what we would see, and I am. And I'll give you a taste of that in a bit. And we'll eventually get at the end to this beautiful image here, which was just taken with the telescope about 2 weeks ago, this color image here, and this beautiful spiral galaxy, which really all I can tell you about it because I don't study those galaxies, but it's really awesome to look at. All right. So we can go back a little over a year in the past. On Christmas Day of 2021, this telescope launched. This telescope cost $10 billion. It's a lot. It's kind of a drop in the hat, given the federal government budget. But it was an international partnership, primarily NASA. The European Space Agency, ESA, launched the telescope. And I used to joke that if it exploded, which it didn't, so we can joke about it now, they would have to pay for another one. But fortunately, it didn't. The launch was perfect, which is important for a variety of reasons. And it was designed to answer a variety of pressing questions about the universe. Most pressingly, when did the lights turn on in the early universe? When did the dark ages end? The reason why this telescope happened and worked is due to the dedication of thousands of scientists and engineers, and both people lobbying politicians and politicians for actually funding it. It was on the chopping block several times I was actually at a conference in Baltimore about this telescope. At the time, it suffered a major delay, and it almost got canceled. And there was a huge public outcry, actually, at that point. This was in, I think, 2011. Huge public outcry that saved this telescope. And astronomers around the world, including many of us here at UT, have really based their careers on the success of this mission. So you can imagine as that happened, we were all a little tense. This was during COVID, so we were all at home watching on Zoom. So this is a screenshot of folks in my collaboration, of my friends and colleagues, and some folks here at Austin watching during launch. We all look pretty intense, again, because if it doesn't go well, what are we going to do? Not only with our own research, but what is NASA going to do? You can imagine this investment was huge. There was, not uniform appreciation in the astronomical community for this telescope because it did take up a sizable portion of the astrophysics budget. And if it had not worked, it would have been really hard to spend so much money on a telescope. Because it's been successful, NASA is already accelerating plans for the next space telescope. The next one, the Nancy Grace Roman Space Telescope being built, will launch in 2027. Got to do amazing things. The next one has been dubbed the Habitable Worlds Observatory. And it's actually going to be a JWST-sized telescope, but to study ultraviolet and optical light, to look for Earth-like planets around other stars and truly characterize them, something that we can do a bit with JWST. But JWST was not designed for that. It was designed to do the things I do and I'm going to tell you about, which is really early galaxies. Turns out it can do a lot in exoplanets as well. We won't talk too much about that today, but there's a lot of exciting results that I'm sure you'll hear in a future BOV meeting from our exoplanet scientists. So launch went amazingly well, so well that the fuel left on the telescope should allow it to maneuver and keep its position in space for over 20 years. The mission requirement was 5. So at the time it launched, we didn't know if we had a 5-year, well, 0-year telescope, if it didn't launch well, a 5-year telescope, or a 20+. So that went great. But it had to unfold. This is the telescope here, and this doesn't look like any picture of this telescope you've ever seen, and that's because it had to fit in a rocket. That's why all future big space telescopes, if we're lucky, we'll build them in space. May end up actually being cheaper. But this one didn't quite have the technology yet, so we had to build it on the ground. It folded up in the rocket. At this point, this is, 20 minutes after launch. We're actually still on Zoom. We were recording our Zoom for this Netflix special, and I had turned off the recording because we were just talking and nothing exciting was happening. And we knew that there's about 300 movable parts in this telescope that have to work in sequence, all single-point failures. If they don't work, the telescope doesn't work. And we had no idea that we were going to see the first of these movable parts happen on camera. This is a live, not live now, but at the time, a live view from the rocket. The telescope had separated from the rocket, and we saw the first solar panel deploy from the telescope. And so that was like, I don't want to get too emotional, but that was extremely emotional to actually see that. I was shocked. And I actually wanted to read you this quote from Jane Rigby. She's the JWST operations project scientist, amazing human being, amazing astronomer. She works at NASA Goddard, was in the room when this was all happening. And she wrote a blog. If you search JWST NASA blog, it's an amazing resource. A lot of the images I'm going to show you on the next few slides are from there. And she wrote about the feeling of being in the room. So I'll just read it. She said, the second stage shuts down and the launch vehicle separates. The call comes out that the attitude control system is working. The solar array should be deploying automatically. That's what we just saw here. There's a tense wait. And then the call, sun is on the array, current is on the array. And she said, suddenly it's deafeningly loud on the voice loops with clapping and shouts of happiness echoing throughout the mission control. I look up to see the video feed from the launch vehicle, and there it is, our beautiful observatory with its solar panel all the way out, shining in the sun. And so you can just imagine the sense of relief amongst these scientists, engineers, all of us. There's still 299 more movable parts to go, but we've got currents. We can actually communicate with the telescope. So that was fantastic. So launch went extremely well. Unfolding went well. We're all here today talking about science, so we know it's working. It took about 3 weeks for the telescope to unfold and get to its final resting place at L2, the second Lagrange point. It's a semi-stable gravitational position in space. It actually goes around the Earth with the sun, but it's about 1 million miles further away from the sun than the Earth, so that it can keep the Earth, the moon, and the sun behind it. You'll see when we see a picture of the full telescope, it has this enormous tennis court-sized sun shield. It's not just a sun shield, it's a sun, Earth, and moon shield. It's an infrared telescope. The Earth glows at infrared wavelengths, so it wants to block all that out. So it's kind of keeping pace with the Earth around the sun as we go. Once it got there, this was, early, mid-January of 2022, so a little over a year ago, we had to commission the telescope. As much as we want to do science right away, we need to focus the mirror, test everything out. It actually had to cool down. It took a long time for the telescope to cool down. And so over the next 6 months, from December to June, the telescope was commissioned. And we waited and waited because, of course, we want to see data. There was a lot of action on Twitter, astronomers following the website that had how many miles away it is and what's happening on the telescope. But we wanted to see an image. And so the wait was worth it. This was one of the first images from the telescope. This is actually one star. And what you're seeing is one star reflected off of each of the 18 mirror segments, each of which are out of focus. But this is what you need to start focusing the telescope. The first step they had to do was actually identify which reflection is coming from which segment. Because the telescope has 18 hexagonal segments. You can move them all, and you want to move them to make them as if they were sort of one mirror with the right shape. But we have to know which one we're moving. So you move one, you can see which star moves, so on and so forth. And so eventually they figure out, it's probably a little hard to read, there's a number and a letter over each of these stars that's labeling which mirror segment it was. And once they figured out that, then we could actually align the images and focus the telescope. But why were we so excited to see this out of focus image? For me, it was that the light path worked. The telescope could collect light and put it onto the instrument. Everything is kind of downhill from there. And I had a real worry about one particular aspect of this light path because I saw the telescope in real life in October of 2019 at Northrop Grumman in Redondo Beach. I got to go give a talk like this to the scientists, which was amazing. And not only again, about emotion a little bit, I failed to imagine how emotional it would be to see that telescope in real life. This picture does not do it justice at all. It is gigantic. But if you look really closely, you can see in the middle of the telescope mirror, kind of a black region, that's where the light actually needs to go down to get to the instruments. So a secondary mirror assembly will deploy, light will bounce off the primary mirror, hit the secondary, come back through the middle. But there's this little red thing there. And if you zoom in a little bit more, here's a closer view. I did not take this picture. And we'll zoom in. I don't know if you can read that. It says, remove before flights. If that was not removed, we are toast. So I actually asked when I was there, and they said, oh, yes, it actually stays on until it got to French Guiana in South America. Somebody's job was to take it off. And I actually did see a blog post or a tweet or something when that happened. So that was a great relief. This was another unexpected image, a selfie of the primary mirror. There's a special lens somewhere in the light path that lets us collect this. And you can actually see one of them is glowing pretty brightly. That's actually the reflection from a star. And so they were able to use this selfie camera, as you were, to figure out which mirror is moving. And then eventually we can focus the stars. They're not quite there yet, but they're getting there. And then we get it all at once. So now all of the 18 segments are aligned in a way to put the star from each segment at the same place. And that's how we collect the light from 18 individual mirrors as if it was one big 6.5 meter diameter mirror. So this came out, let's see, February 25th, 2022. What is today? Today is February 25th, so 1 year ago today. That's amazing. Yeah, so this was cool. This was even cooler. So this was a press image they did actually of that image. And what I remember thinking when I look at this is not the star, star's fine, but all those little dots in the background. Those are all galaxies, many of them probably somewhat distant. Any focus image you have ever done with a telescope before this, I don't think you're seeing galaxies, at least not anything outside the local neighborhood. So this already, before we had any numbers, any quantitative metrics, tells us this thing is working pretty amazingly well. So well that astronomers around the world downloaded this in JPEG form and tried to convert it to a science type of image that we use called FITS and tried to do science on it. I guess I was not quite that crazy, but it was very exciting. So this was just sort of our first hint that things were going well. This image came out April 28th, 2022. This is actually showing you the full focal plane of JWST. And you can see 1, 2, 3, 4, 5 instruments. There are 5 instruments. They all have their specialties. We'll talk a lot about NIRCam, which is this one in the middle. That's sort of the workhorse camera, most analogous to the cameras we're used to on the Hubble telescope. But it's actually showing light hitting all of them and being recorded from all of them, which is great. And everything looks amazing. This is a sharpness check. We want the stars to be as small as possible. Stars do have a finite size. They're actually quite big in terrestrial terms. But they're so far away that by the time we receive their light from Earth, they're what we call a point source. They're kind of almost infinitesimally small with the telescopes we have. And so we want to make the stars as small as we can in our cameras. And that means that when we look at way more interesting things like galaxies, we can see them in great detail. And so that is working very well. Telescope very, very sharp. So advance a few more months, And it's time for science images. So this was on July 12th of this last year of 2022. The telescope had actually started taking science data in late June. I'll tell you a little bit more about that later. We'd actually already received science data for our SEARS program. We didn't get to see it yet. It was embargoed until this happened. And it was only a day or two before this event that it turned out the president actually wanted to be the one to introduce the data. So this was a fantastic event that was live streamed, where the president, vice president, and folks from NASA and the Space Telescope Science Institute got to show us the first images from the telescope. And I'll show you some of these first images. These are called early release observations. They were designed for like the wow factor, not necessarily for science, but it turns out you can do a lot of great science with them as well. And so you've probably seen this one. This is actually probably my favorite one that's not like an early galaxy deep field. This is the Carina Nebula, a star-forming region in our own galaxy, where the sort of brown wave-looking feature is gas and dust, where young stars are forming as we speak. This is the Southern Ring Nebula. This is a planetary nebula. This is what stars like the sun do at the later stages of their life. They blow off their outer layers and make them glow quite prettily. This has nothing to do with a planet, but if you looked in a telescope 150 years ago, at that time, this would kind of have looked like colors and shapes of Jupiter in your eyepiece. And so we could kind of, I wasn't there, but the astronomers at the time could kind of tell that it was a little fuzzy, so it probably wasn't a planet, so it was more nebulous, but it looked like a planet. So the name Planetary Nebula was born. We still use it today. This is Stephan's Quintet, a group of interacting galaxies. The most stunning thing about this to me is, again, if you look in the background, it's full of galaxies. In fact, one of the most distant galaxy candidates that's been found so far is in this field, in this Stephan's Quintet field. You might remember this field from the movie It's a Wonderful Life. These were the galaxies that were like the angels talking. If you watched that a couple months ago, like I did. Tried to get my kids to watch it. They were not into it. And finally, SMACS 0723. This is a galaxy cluster, so sort of a cosmic metropolis of galaxies. And what you're seeing, the big bright things, those are galaxies that aren't all that far away. Again, far in terrestrial terms, but not in astronomical terms. But in the background, all the tiny little dots are distant galaxies. And some of them actually get magnified. Galaxy clusters are really cool because they act like giant cosmic magnifying lenses, and they can actually bend and stretch and magnify distant galaxies. And so if you look really closely, you can see that little thing there. Kind of looks like a slug. That's actually a really distant galaxy here that's been stretched out so you can see it in greater detail. And so that's really exciting. So the images were stunning. And they were designed, and the data coming in from this telescope, across its whole mission, but especially early, is designed around 4 key science themes. The first one is first light in the universe. Science goal number 1 of this telescope. Again, when did the lights turn on? When did the cosmic dark ages end? Galaxy assembly. How do galaxies form their structure? When we look at our Milky Way galaxy, it's a beautiful barred spiral galaxy. How does that happen? When does that happen? Star life cycles. We already saw some of those images. How do stars form? How do they live their lives? How do they die and beget new generations of star formation? And other worlds. This was a late addition because it wasn't until the early to mid-90s that we really had good conclusive proof about planets around other stars. Some of that work led here by our own Bill Cochran at UT. And now that is taking up a good chunk of the telescope's time because there's lots of exciting science we can do about exoplanets. But we're going to talk mostly about first light because that's what I do, and that's why we're here today. So what do we actually mean by first light? So let's do a little bit of a primer about the early universe. We'll go back to the beginning and sort of introduce our cosmic timeline. So at the beginning, there was nothing. To the left, time equals 0, kind of blank. At some point, there was nothing, and then there was a universe. We call this event the Big Bang. Since then, science observations can explain everything that has happened fairly well. Today, we exist off to the right at a time 13.8 billion years, or gigayears, later. In today's universe, you've got big galaxies, small galaxies. The big ones can be kind of pretty. They're spirals, they're ellipticals, lots of complex things going on in today's universe. So sort of how do we go from nothing to all of this in 13.8 billion years? Well, astronomers have been around for a while, for thousands of years, and we've learned some about what's happening. First of all, we have studied the cosmic microwave background radiation. This is the leftover light, or you can think of as heat from the Big Bang. The light we see from that comes from a time about 400,000 years after the Big Bang, and it's like an immense baby picture of the universe. and it tells us how the universe was seeded with structure. It helps us learn how much matter there is in the universe, really our underlying cosmology, the structure, the backbone of the universe. We can learn from that. On the other hand, we can take telescopes both on the ground and in space like Hubble, and we can do pretty well over about the past 10 billion years of cosmic time, and we learned that it wasn't until a time we thought, about 3 billion years after the Big Bang, that big mature galaxies like our own Milky Way had formed. And so for the last 10 billion years, I could say not a lot has happened. That's not quite true, but a lot had already happened before 3 billion years. So if we want to understand how big galaxies form and evolve, we have to go to yet earlier times. And so the limit of, that's today's, that should be yesterday's telescopes. The limit of telescopes before JWST is about 500 million years after the Big Bang, or 13.3 billion years into the past. And there is a lot that happens in this last little slice here from 500 million years to 3 billion years. Galaxies go from small to big, certainly. But we still see galaxies. At the limit of the Hubble Space Telescope, we can find galaxies out there. They're coming from this time only 500 million years after the Big Bang, but we need to push farther. We want to push further back into cosmic time, closer and closer to the Big Bang, so we can find out when did galaxies actually first form. We have not yet hit that limit with the Hubble Space Telescope. And so we really want to know, when did the first galaxies form out of the cosmic dark ages? The cosmic dark ages is a name that we give to the period of time between the Big Bang and when the first stars and galaxies formed. There was light, that leftover light from the Big Bang, but there was no light coming from stars. And the universe actually got quite dark and cool during that time. We expect there to be some delay between the Big Bang and the first stars, because to form stars, you need really, really cold gas. And right after the Big Bang, the entire universe was really, really hot. It started cooling immediately, but our best guess is that it would take somewhere from 100 million years to 400 million years for stars to form. So that's kind of our window for the cosmic dark ages. So why should we care? You all trudged down here or turned on your YouTube, so I'm probably preaching to the choir a bit about this one. But I often get asked, like, why should we spend money studying galaxy evolution, right? And so for me, my best answer is that this really defines the human story. Everything that we see around us in this room, in our solar system, was formed in stars. Every single element other than hydrogen and helium. And so by looking to the earliest times, the first galaxies were the first time in the universe that heavy elements had formed anywhere, ever. And so by looking for the creation of these first elements, we're identifying really the first chapter of the very long 13.8 billion year story that ultimately led to human existence. All right. So how do we actually do this, practically speaking? Here's a beautiful image. This is that early release observation galaxy cluster image. How do we actually find distant galaxies in these images? What we want to do is we want to look for small red dots. You can probably find some with your eyes right now. Even on this projector's okay. Looks better on my computer screen. You can download this image like a 200 megabyte version. It's great. So we want to look for small red dots. So why small? That's a little bit easy to understand. They're really far away. And as things move farther away, they get smaller. And we're looking at the early universe. Galaxies haven't had time to grow big yet. So that's sort of why small. Why red? That has to do with the expansion of the universe, which is something that we first learned about almost exactly 100 years ago from astronomers like Edwin Hubble, who noticed that when they made a plot of the distance to galaxies, that's on the horizontal axis here, to the velocity that those galaxies were moving at, that's at the vertical axis, all galaxies were moving away from our own Milky Way. Not only that, but the more distant ones were receding more quickly. And this is actually what you would see if you lived in an expanding universe. We are not actually at the center of the expanding universe. You could jump to one of these other galaxies, make the same measurements, and you would see the same thing. All of space is expanding on intergalactic scales, okay? On galaxy scales, solar system scales, on the Earth, gravity rules on small scales. We're being held together, so don't worry. But galaxies themselves are actually being spread apart due to the expansion of the universe. So that's kind of cool. And we can couple that with a feature of this expansion, which is that as light travels to us from any object, really, it's actually getting stretched as space expands. It's very similar to the Doppler effect that you're probably most familiar with sound, with like a police siren. As it goes towards you, the sound goes up in pitch, and as it goes away from you, the sound gets lower in pitch. And it's all about how quickly are you receiving those sound waves. In this example, it's how quickly are we receiving the light waves. So because all objects are moving away from us, they all look redder than they would if they were not moving at all. Okay, so that's sort of redshift in a nutshell. And the redder they look, the farther away the galaxies are. So small red things. That's what we're looking for. Astronomers like numbers, so we give this redshift a number. It's a unitless number, which means it's kind of meaningless. But I'll give you a few scales. Today we exist at redshift 0, okay? If we are looking at a galaxy at a redshift of 1, it means all of the light we receive from that galaxy, its wavelengths have been doubled. So all the light waves have been stretched by a factor of 2. And that is looking back, actually already over halfway back towards the Big Bang. So the left column of this handy table here is redshift. The right column is time since the Big Bang. So we are here 13.8 billion years since the Big Bang. And then by redshift of 1, you've already gone over halfway back, only 6 billion years since the Big Bang. The limit of the Hubble Space Telescope is about a redshift of 10, which goes to this time, that sort of limit of 500 million years after the Big Bang, or 0.5 billion years. Sort of 0 to 10, we've done well. Redshift beyond 10, that's kind of the vast unknown. Definitely not everything is solved from redshift 0 to 10. Lots of exciting things to do, especially with JWST. But of course, the first thing we want to do with this fancy new telescope is, can we push beyond a redshift of 10? Okay, so just a summary, by measuring how red-shifted a galaxy's light is, that tells us how far away it is. I often get asked, how far away is this galaxy in miles or light years or whatever? And I never know the answer. What I always think of is time. When in cosmic history am I viewing this galaxy? And that really helps us put together the story. Okay. So we can measure redshifts very precisely if we take a spectrum. If you take light from a galaxy, pass it through a prism, and split it apart into its component wavelengths. We'd love to do that. We will do that. I will show you that. But we can also estimate it pretty well from imaging alone. And that's fantastic, because some images, like some of the ones I'll show you, have tens of thousands of galaxies. And we can estimate the redshifts to every single one from these images. With a spectrum, you can only do that for 1 at a time, maybe 20 or 30 at a time. So they're very complementary. But we're going to do a lot of this with imaging today. All right. So we'll come back to this plot a lot. This is a plot of redshift on the bottom horizontal axis. And because redshift is the same thing as time, on the top, I put time since the Big Bang. Okay? So we're really going to hone in on that first 500 million years. That's the exciting frontier. The vertical axis is brightness in these weird astronomer units called magnitudes. You can kind of ignore that. Just know that bright is up here and faint is down here. Okay? So brightness versus time. All right. There we go. And these are the cosmic dark ages, or that's our window for the cosmic dark ages, sometime between 100 and 400 million years after the Big Bang. So how well could Hubble do? All right. I have been working on the Hubble Space Telescope for a while, but for the past few years before JWST launched, I really focused on trying to push Hubble to its limits and see how many galaxies could we find at redshifts 8, 9, or 10 with Hubble. So that's really the left edge of this plot. And I will show you what we were able to find here. I'm going to show you 2. Each of those tiny little dots is a galaxy, okay, an incredibly distant galaxy. The one outlined in blue actually had its redshift confirmed with a spectrum from our own graduate student Rebecca Larson. This was work she did with the Keck Observatory 10-meter telescope. The one in red I'm going to come back to at the end. Something very interesting about that one, also done by Rebecca Larson. So we'll come back to that. All right, and these are the rest of them. There's like about a dozen or so that we can find. Okay. The most distant one is the one that I've sort of shown you the color image of. That one has a name GNZ11. It's in the field called Goods North, a well-studied field of the sky. Z11 because the first estimate of its redshift was about 11 or so. And that's it, really. Probably a few more out there I forgot about, but that's basically it. So a small number of galaxies, and they're all pretty bright, right? They're all kind of at the top end of this plot. If we look at a prediction from a simulation, there should be tons of fainter galaxies out there, but we just couldn't see them because of the limits of Hubble. Hubble is fantastic. I love Hubble. But the primary mirror of Hubble, which sets its light gathering power, is 2.4 meters in diameter. So like the height of your average NBA center, which is tall, again, in human terms, but not that big for telescopes, right? JWST has a light gathering power 7 times larger, so it should be able to see fainter. Likewise, we're limited in this, so that's sort of the vertical limitation here, why we can't see anything below this line. We're limited in the horizontal axis. We can't push to the right, because once you get past about a redshift of 10, all of the light that you would receive from these galaxies has been redshifted so much, it is no longer observable at visible wavelengths. You need an infrared telescope. In fact, Hubble has a little bit of infrared capabilities, and that's the only reason why we could find these. But it only does what we call the near infrared. We need to go into the real infrared, or sometimes called the mid-infrared. And that's what JWST was built to do, okay? So this is sort of how things looked basically before July 14th, 2022. That was when the scientists could finally download the data that had been taken. All right. So we'll go through this quickly because I just said it. What does JWST bring to the early universe? It's bigger, more light gathering power. We can see fainter stuff. That's easy to grasp. And the second one is the wavelengths. We really want to see infrared light so that we can see more highly redshifted galaxies. That's how infrared light helps us with the early universe. Infrared light is fantastic for a variety of other things. Locally in our own galaxy, you can peer through dusty clouds and see stars in formation. So that's another example of why infrared is great. So that's why you may have heard to JWST, we never call it a Hubble replacement. Number one, Hubble's still going. Hubble's fantastic. But it's not actually a Hubble replacement. Hubble works primarily at ultraviolet and optical wavelengths. That is fantastic. We need a UV optical space telescope. And in fact, once Hubble breaks, which probably isn't, unfortunately, too far into our future, we're going to have a big gap in our capabilities. All right? That's a whole other talk about future telescopes there. There are plans. They're coming along slowly. But now we can at least do the infrared. So we have this fantastic infrared telescope. All right. One more redshift plot. This is just another way of sort of splitting the time in the universe in two. We could see up to redshift 10 with Hubble, but we still have a lot to learn with JWST because of the resolution. The level of detail you can get in an image from a telescope also depends on how big the mirror is. A bigger mirror means you can see finer detail. And so I'll show you an example of that a little bit later. And at redshift greater than 10 or so, couldn't do it at all, really, until we got JWST. And now we can do it. This is a picture of a city I'm being told is Austin. This picture was taken actually almost 10 years ago. And so I don't know, there's maybe 10 more skyscrapers in the background there. The full-scale model of JWST was fortunately brought here at a South by Southwest exhibit by NASA, Northrop Grumman. So this was a fantastic event and really actually gives you an idea of the scale of the telescope. There are people there around the bottom, actually some of our graduate students at the time. So this thing here is about the size of a tennis court. This here is about 6.5 meters in diameter. So it's truly enormous. All right. So coming back to our story of the telescope, it works. That's great. Who gets the first data? All right, everybody wants data. We all want to see what's going to happen. So of course we knew there was going to be so much to learn. So the director of the Space Telescope Science Institute, which is the place who runs Hubble and now runs JWST, agreed to give 500 of some of the first science hours of the telescope to sort of all areas of astronomy. And they had a competition for what they called early release science programs. Okay. Like all telescopes, JWST runs through a competitive peer review process. That means if you want time, you have to write a proposal for as compelling a science case as you can. You have to say, why is this exciting? Why do I need this telescope to do it? Why can't I do it with Hubble or a ground-based telescope? And in this case, you also had to say, how is my data going to benefit the community? Why should your observation be first, right? The best ideas win. And like with any good telescope, it's incredibly oversubscribed, meaning there are way more ideas submitted than there is time for. So of course, we were very interested in this. We've been waiting for this, myself, my collaborators, for a while. So we formed a group of about 100 astronomers around the world and basically did nothing else other than teach. We still taught from October 2016 until August of 2017 to write this proposal. And so we worked incredibly hard. 10 months? Yeah, 10 months. A long time to write a proposal. But I knew that 106 went in, and they were only going to pick something like 12 or so. So it's a little bit dicey. But fortunately, we were successful. And so this is our fabulous logo. The name of our survey is the Cosmic Evolution Early Release Science Survey, or SEARS. And we had several goals. The first one is what we've been talking about. Let's push our cosmic horizons back to see what is happening in the first 500 million years of the universe. But we don't just want to do one thing, or we never would have had a chance in this competitive landscape. We had to promise many things. So we're actually using several of JWST's instruments. And beyond looking for early galaxies, we're going to use JWST spectrographs to study the natures of some of the first stars to form in the universe and search for the presence of early supermassive black holes. And then we're going to use JWST's excellent resolution to study the structure of galaxies. And so we'll talk most about bullet point number 1 in the next bit, but we'll touch on the other two as well. Okay. So by the time JWST launched, it launched late enough. I don't know if you remember. It was well, I don't remember when it was originally supposed to launch, like 2010 or something. But when we got to 2021, we thought it would launch in November. Then it got pushed to early December. Then it got pushed to December 24th. And then it finally launched on December 25th. At that point, I didn't think it would be commissioned in time to do our survey in June. Our survey, for a variety of reasons, had to be done in June or December. So we were sort of designed to it coming in December, and we wouldn't be first, and fine, whatever. I was sad, but it would be okay. And then I got this email on June 9th. I remember this vividly. I was in a cafe in Riverside, California. I was visiting UC Riverside to give a colloquium, and it was the day I was leaving, so I was having coffee. And I got this email that was like, we can do up to like 25 hours of your program. Tell us what to do like now, effectively. And so we spent the next couple days like rapidly trying to split our program in two because it was a 70-hour program. And so we ended up being able to get 25 hours of our data in June, where we got part of our imaging, and everything else we got in late December. And so this is the first epoch of SEARS. This is actually showing 4 individual pointings with the NearCam camera. Again, you can download the 300 meg version from our website, sears.github.io. I definitely recommend it. Like, book a couple hours. You will spend a lot of time zooming in, going around there. OK, so what are we learning, right? That's what we're going to spend most of the rest of the time talking about. First of all, the universe is pretty. We look at the nearby galaxies in this image, and when we as astronomers, we actually put this up at the big viz wall at the Texas Advanced Computing Center, we're running around looking at all the spiral galaxies. And that's not what we actually do for our research. We study the small galaxies. They're fun to find, not that impressive to look at. But the spiral galaxies look amazing. The structure that you can see simply blew us away. You can like count the individual star clusters in these galaxies, which is great. We could see interacting galaxies here. A supernova went off there. We found it because there was an arrow there pointing at it. And then another galaxy with lots of star clusters. This one is just this really cool alignment that Rebecca calls the Pac-Man galaxy because it looks like Pac-Man eating all the little dots. And another galaxy overdensity here that we actually just submitted a paper on, an astronomer in our team, Rose Coogan. Again, great. Let's look for the faint red stuff. So we'll zoom in a bit. And I should say that when we first downloaded the data, it did not look like this. It was, for lack of a better word, dirty. There are a lot of instrumental effects you have to take out. And this was the same day that everyone got their data. So nobody had the answer. And so we were rapidly trying to make it better. And we had planned to try to write a paper on early galaxies, but we thought it would be a while. We said we will only publish something quickly if it is like irrefutable, if we know that no matter what we do to improve the data, this galaxy will stand the test of time. Okay? And so we were looking, can we find any galaxy that looks like it's really far away and looks pretty good? And we arrived at this little red dot right here, which if you're a BOV member is on the cover of your program. So what is this galaxy? It looks very red with JWST even, so it must be at very high redshift. And so we looked into it. We first found this galaxy. So I basically have a code that takes the data, does a bunch of stuff, and spits out a list of early galaxy candidates. And this one I actually had to go back and see. It was actually in my list on July 18th, which was my birthday, the first time we looked at it. And as we made the data better, I think we had 3 improvements during the week. On July 22nd, we looked at the list again, and I'm like, this one is still there. I showed my colleagues. We were actually in a room here in Austin. Fortunately, it was the summer, so like a windowless room, a nice cool windowless room in Austin in the summer. And we convinced ourselves this was a galaxy at a redshift of about 12, meaning that we're seeing it at a time 370 million years after the Big Bang. So more distant than anything humans had ever seen before. And so that was a Friday night. I went home. I don't remember what happened. And then I woke up Monday, and we basically had a paper draft done. Apologies to my family for that weekend. They've been very, very accommodating. And so by Monday, we had a submitted paper. We took a little Star Wars theme from the reference. A long time ago in a galaxy far, far away, a candidate redshift 12 galaxy in early JWST SEARS imaging. The funny thing about this title, right before I submitted it, my wife Keely, who's a professor in the department as well, said, you should see if anybody else has used that same Star Wars reference. So I said, OK. So I type into we have a fabulous literature search tool. And I search this, and I come up with a poster from, I think, 1985 from our professor, Craig Wheeler. And so I emailed him, and I said, do you mind if I also use this title in my paper? Here's the paper. I will show it to you ahead of time. And he said, yes, yes, of course. So not the first to come up with a Star Wars reference, but really excited to do it. So what did we call the galaxy? That's part of the story as well. July 22nd happened to be my daughter's birthday. And so we named it Maisie's Galaxy. I sort of did it as a joke. We had like a long phone number name based on the position of this object in the sky. But right before we submitted it, my colleagues were saying, we should give this like a punchy name, so like a catchy name, so people will use it. If you just use a phone number, they're never going to say the name out loud. And one of my colleagues said, what about Maisie's Galaxy? Steve like kind of referred to it as that. And I said, well, I'm not going to argue. She actually wanted me to name a galaxy after her. She was almost going to be here today, but she had a Girl Scout field trip to the zoo in Waco last night, and they're not back yet. So she will maybe watch the recording. Maybe she loves YouTube, so we'll see. OK, so Maisie's galaxy got a lot of attention, being one of the first galaxies at this early time ever seen, and some of the first results from JWST. So we have our own fabulous CNS press team had this press release here. We got on local TV on KXDN. She was very pleased to see that. But it made it wider to the New York Times and lots of other websites and radio shows and TV shows. It made it in front of the US Congress. That was exciting. Volker talked about this earlier. That was kind of a surreal experience to get to go there and talk about the performance of JWST and what I'm told is one of the more collegial Congress environments where they were just kind of celebrating the science, no hard-hitting questions. And then some of you probably saw this earlier this week on the PBS Nova special, New Eyes on the Universe. So that's fun. It won't lie about that. But of course, we're scientists. So what are we actually learning? So the image here on the left, that's my attempt actually my colleague Casey Papovich, professor at Texas A&M. I don't know if there's any Aggies in the room. We do work together, well, off the field at least. That's his version of the color image. So the left is sort of a true color image. It's very red. The one on the right is what would you see if you were right next to this galaxy? If we could remove the red shifting of the light. What color is it intrinsically? It's very, very blue. And that gives us a hint as to what's going on. If you have a galaxy that's really blue, it means it must be full of hot, young stars, probably very, very massive. And so we'll come back to that, but that's our first hint that these galaxies are quite different than what we're used to seeing. And we found one. This is my favorite plot. It's comparing different theoretical predictions for how many galaxies we should have found in our survey. So each bar is a different model, and then the horizontal line up here is 1. This is actually a log plot, so if it's below the line, it's below the line by a lot. Basically, none of them matched it. And so the fact that we found 1 was unexpected. The formal uncertainty on 1 is 1, so we found 1 plus or minus 1. So it's actually not that important that we found 1 and not 0, but it tells us that if we can continue to find more of these, maybe something interesting is going on in the early universe, and really maybe something unexpected. All right. So here we are in our windowless room. This is us celebrating, definitely not with alcohol on a public college campus, after we found the galaxy. And then we got to go visit the Viz Lab. This is myself and Pablo Arbajero, who's a postdoc in our lab, actually looking at the image on my laptop, trying to find Maisie's galaxy on this big giant screen there. And I should say, this collaboration of people I'm working with at the SEARS team is a fabulous collaboration. I love the people in this group. It's one of the reasons why we work well together. And it's really why we're able to do these results so quickly. It's not one person or even just our small group here at Austin. It is this group of over 100 people from around the world. All right, so let's come back to our cosmic sort of gallery here. Here we have everything. Hubble's fantastic, but it was limited, right? It could do. Here's Maisie's galaxy there. We're in that gray region. We're in the cosmic dark ages. Well, we're actually not in the cosmic dark ages. It means they must have ended earlier than this galaxy because we found 1. Okay, so is Maisie alone? Are there any other galaxies we can find? It took us a little while to be happy with the quality of our data. A whole other conversation about how do we calibrate the telescope was not all that well calibrated right off the bat. We worked on that. So by about mid-fall of last year, we had our answer. And in fact, we found about 25 friends of Maisie. Some of them at sort of Hubble accessible redshifts, but you'll see some more pop up out at higher redshifts. Yeah. Including this one here at a redshift of 16.5. If you were here for Seiji's talk earlier, this is the one he mentioned that we thought it was so high redshift and so incredibly bright, there's no way it could be right. It must be a dusty galaxy at low redshift. So it looks red because it's just red, not because it's high redshift. But Seiji led some observations with the NOEMA sub-millimeter telescope, and it turns out it doesn't look like a dusty galaxy. We will actually get a spectrum of this galaxy at the end of March and measure the precise distance. And if it is truly at a redshift of 16, something incredibly crazy is going on. And I have some ideas about what that might mean. Not actually, I don't want to be too crazy. Like, we'll get to it. All right. The Big Bang isn't broken. Like, cosmology's not broken. It's fine. We can explain it with just stars. I will tell you, but weird stars. Okay. So does this, really high abundance of early galaxies match our expectations? This is another version of that bar graph plot showing number of galaxies versus redshifts. Each of these little curves is like a different model. This reminds me of those hurricane spaghetti plots we're used to seeing here in Texas, where like if it's like the next day prediction, the lines are close together, but when you get 5 days in the future, they spread apart. And that's kind of what's happening here. If we look at a redshift of 12, these models differ by sometimes a factor of 100. And that's because there were no observations. They had no idea what was happening. They were just making their best guess. And these data points are from SEARS. We sort of put our results in 2 bins. It's high. It actually matches one model. That model's probably wrong. I'll tell you why later. It's exciting, though, that it matches. But so we're pretty much in excess of any physical prediction for what would happen at early times. This is another way of looking at it. This is what we call a luminosity function. So this is showing the number of galaxies that you see in a volume of space as a function of brightness, where faint is on the right and bright is on the left. Okay? And these are actually showing results from pedestrian redshifts of 5, 6, 7, and 8. And you can see it has this sort of characteristic shape, lots of faint galaxies, not very many bright galaxies. But every redshift we increase, it kind of decreases by a smooth amount, right? We could then go to redshift 9. This is work that myself and my postdoc, Michaela Bagley, did with Hubble. And it looks to, there's a lot of scatter, but it looks to continuously go down. So if we extrapolate that to the SEARS redshifts, the redshifts we can now do, okay, we sort of picked redshift 11 as our average redshift of all the exciting redshifts. This is where we would expect to find galaxies if it follows the expected evolution. You can probably already guess, based on the left plot, it doesn't. This is actually what we see. It's too high by a lot and by a significant amount. And it's not just us. There's more data coming out now, including from Cosmos Web, and we are seeing this repeat itself over and over again. And so this result does appear to be robust. So we're sort of left with two choices. Are there too many galaxies, or are the galaxies just too bright? And so if you've been following the press on some of these results, you may have seen phrases like the Big Bang is broken, dark matter doesn't exist, all these sort of crazy ideas to explain why are there too many galaxies. That's not impossible, but I actually don't think that's the most likely outcome. I think that the galaxies are just brighter than we expect them to be. And there's a really easy explanation for why that would be, which is that when we predict what the first stars to form in the universe would look like, or the first galaxies, so Department Chair Volker Braun has been doing for his entire career, you would predict that they would be filled with really massive stars. These really massive stars would be hot things are bright, and they would be blue, because hot things are also blue. And so you would expect to see galaxies filled with bright, hot blue stars. And what did Maisie's galaxy look like when we looked at it after we de-redshifted it? It was blue, right? So that story kind of holds together. So what if there's not too many galaxies? What if the stars are just more massive and hotter than the models are predicting? And that is fully in line with what we think should happen in the early universe. And that's really driven by a low abundance of heavy elements, which also makes sense because when the Big Bang happened, there was only hydrogen and helium. And if you form stars out of just hydrogen and helium, you'll end up with massive hot stars. Okay? Even the next generation of stars, they maybe have very low abundance of heavy chemical elements. They will also be pretty hot and blue. And so do we know that this is the answer? Absolutely not. But we just had the deadline for the next year of JWST proposals, and our collaboration put in a proposal to take spectra to actually look for evidence that this is what's going on. So being scientists, coming up with ideas, maybe it is that cosmology is broken. I don't know. We'll see what we see. But I don't think that's the most likely answer. We have an easier answer that matches our expectations. OK. All right. Since then, December has come and gone. We finished the SEARS survey. This is actually our full mosaic of 10 pointings with the NearCam camera, basically 2.5 times larger than what we saw previously. I literally just got this yesterday, so this is not on our website, but it will be there soon. Okay? And this data reduction was led by UT postdoc, and I hope they won't mind me saying this, JWST data wizard, Michaela Bagley, who's a senior postdoc in my group, and really one of the most knowledgeable people on the planet about this camera because there was so much to learn about how to make these data work. And so we'll just zoom in again, very, very pretty. All right, and everybody came back to Austin. So I got people to come here in July, and they liked it so much, they said, let's come back when we actually want to go outside. So this is Michaela looking very excited, seeing their mosaic on the TV here in the TAC Viz Lab, walking in the room. This was a group of us staring at spectra. You don't really need a giant screen to look at spectra, but we did it just for fun. And then this was actually the same day they were doing the NOVA shoot. So this is the other side of the camera with Rebecca showing some of her results, holding her dog Jasmine there, who actually made it on TV. This is my good friend and colleague Mark Dickinson, who was actually one of the minds behind the Hubble Deep Field that we heard about this morning, the sort of controversial, let's stare in one spot for hundreds of hours that yielded tremendous results, pointing out something there. And then we had everyone over for dinner that night at our house, including some new graduate student I don't recognize there. It's our dog Lilo. I did not know she was being held up. I saw that later in the picture. Our dog Barley is there on the ground too. You can kind of see him. All right. So let's go back to our gallery here. This was sort of after the first epoch of SEARS, blown away by what we've seen. Now we've got 2.5 times more data. What do we see? This is so exciting. I haven't even published this yet. I hope to at some point. We found the galaxies, but we haven't actually published it. And so we are seeing Maisie, not alone. She's got a lot more friends now. I actually only showed you the ones at redshift greater than 10, but I had a little bit of extra energy a couple nights ago, so I'll add in all the other ones there at redshift 9 to 10. We're starting to not be able to see like the background, right? Yeah. So this is amazing. This is about 100 galaxies, about a third of which are more distant than anything we've ever seen before. And this is from what is a pretty modest size program. It's not a big program. And so what we expect to see from the whole mission is amazing. And there's still one more result to show you here. Okay, so what else are we learning? These data have exquisite spatial resolution. This was a figure of you here may have seen this morning comparing a Hubble observation to a JWST observation of a galaxy. And it looks kind of like Milky Way in shape. It's a barred spiral, but the exciting thing about this galaxy is we're seeing it as it is at a redshift of 2. So we're seeing it actually fairly early in the universe's history. And it's not the only one. There are many barred spiral galaxies. This is a result led by Kei Guo, who's a graduate student working with Sharda Jogi in our department. So Milky Way galaxies form very early in the universe, which is an incredible result. And something, we could see that galaxy with Hubble, but we cannot study its shape. And SEARS is not only imaging, it is spectroscopy as well. We take the light from a source, split it apart with something like a prism into its component wavelengths, and we can learn an immense amount more information from that. And I'll just show you a few key results here. One led by Seiji, who talked this morning. I don't actually think you talked about this paper. You've written too many papers to talk about them all. Seiji led a paper on SEARS spectra of some of those really early galaxies. So we estimated the redshifts in that plot I showed you from imaging, but we would love to take a spectrum and see, really looking for what we would call an emission line, a little spike in the spectrum that we know should be at a particular wavelength, but we see it at a different one, and that tells us how redshifted it is. And we had 10 or 11 galaxies that Seiji studied in his paper. 4 we saw nothing, and that's actually okay. Just means they were faint, and we didn't look long enough. The other 7, basically spot on. All got them at high redshift. So that was great. I was glad that all of these things we're claiming are early galaxies. That actually turn out to be very likely to be. This is another view of spectra. What's incredible here, this little bright blob here, you kind of see that pattern going. That's oxygen that we're seeing in galaxy spectra from a time about 12 billion years into the past up to this one here. It's actually the galaxy that Rebecca had measured the redshift with Keck. Took us like 2 nights integrating on the same source. This is less than 1 hour with JWST, and we get the redshift. And our redshift was right, so that's fun. It's good to be right, most of the time at least. All right, that particular galaxy, that's the one that Rebecca studied there. Okay, so that's exciting. What about massive black holes? I sort of teased we talk about this a little bit. Supermassive black holes are really exciting. I'm told I didn't really get excited about them until recently, until I found out we could study them in the early universe. So they exist today in the centers of all massive galaxies. And it turns out there are supermassive black holes pretty early on in the universe, found with the Sloan Digital Sky Survey at redshifts of 6 to 7, about 1 billion years after the Big Bang. So how do they actually form? Okay, so this is sort of a summary plot showing age of the universe, so early is on the left, and about 1 billion years after the Big Bang is on the right, versus the mass of a black hole. And each of those red dots is a real discovered black hole from the Sloan Digital Sky Survey. Okay? They can't form this massive. They have to form from smaller seeds and grow. And they can grow in basically 2 ways, by combining together and merging, or they can accrete gas. Gas can spiral in, and they can eat the gas and grow in that way. And there's limits to how fast they can grow. And our best ideas of how fast they can grow are given by those lines there. So they're sort of showing tracks of black hole growth. And so the basic question is, if we're finding all of these massive ones, where are their progenitors? There must be smaller black holes out there waiting to be found, just lurking in galaxies, hidden little monsters, if you were, hiding in these galaxies. And so there are a few ways to look for black holes. One of them is to look for really fast-moving gas. Okay, and I'll show you a plot in a second. But you'll notice there are a few different ways of forming black holes. Our best idea, the only way we know you can form a black hole, is from a star exploding. A massive star can explode, and if it's big enough, it will leave a stellar mass-sized black hole, a few times the mass of the sun, and then that could grow. Okay, those would have to start down here. Okay? It's really hard to get to this massive if you start down here. So there's another idea. This is from a paper from some guy, Brahm and Abilov, in 2003, that proposed a different channel, what's called a direct collapse black hole. maybe 100,000 solar masses of gas can directly collapse into a black hole at early times. And then you would start here. And then it would actually be doable to grow into what we can see. So we don't know if this actually happens in the universe. We need to find earlier black holes and ideally smaller black holes to push on these theories. Okay. So let's look for black holes, and we can do that with spectra by looking for really fast-moving gas. This is a cartoon picture, not a real picture of a black hole. Gas that's close to the big massive thing is swirling around really quickly. And what that's going to do is going to take your emission from, say, hydrogen, which would normally be a nice little spike in a spectrum, I'll show you in a second, and it would broaden it, fatten it out, because it's moving. Some of it's moving towards you, some of it's moving away from you. So we want to look for broad emission lines. And so this is a SEARS spectrum from a galaxy. This is hydrogen coming from a galaxy at a redshift of 5.2, okay? And if you look really closely, only because I'm used to looking at this, it's kind of fat at the bottom. It's very narrow up here, it's kind of fat at the bottom. Okay, and if we zoom in, we can see that it looks like this hydrogen has a narrow, sort of regular component and what we would call a broad component. That's this blue line. So this is irrefutable evidence that there is a growing black hole in this galaxy. This galaxy we had actually already found in our image, and we're like, oh, it's a redshift 5 galaxy. We did not think it was hosting a glowing supermassive black hole, and that's because the black hole is pretty low mass, and it's not all that bright. So the stars in the galaxy are kind of outshining it. But that's exactly what should be happening. If you want to grow these big massive things, there must be smaller things out there to find. And so we can go put these results from my colleague Dale Kachevsky at Colby College here. Okay, we found 2 of them. We actually found more. These are only 2 we published. And they're kind of right here. They're lower in mass than these massive quasars, which is exciting. But they're not found at early enough times to be the progenitors of these massive quasars. So can we find earlier supermassive black holes? Okay, so I outlined this one in red here. And the answer is yes. So this is a galaxy up here that has a redshift of 8.7. We've actually known that redshift for 7 years, found with the Keck telescope. And we also see a broad emission line component. You'll notice the signal to noise, or the fidelity of these data, are not as good. That's because this object is much fainter. So ideally, we'd observe it for longer, which we'll absolutely try to do. Okay, so this was a discovery by Rebecca Larson, who's a graduate student here at UT and a US Air Force veteran. Okay, and when we put this object's mass on this plot, somewhere around there. And so now we're actually pushing to earlier times, and we're pushing to the regime where we are seeing the progenitors of these massive black holes. We are not yet able to say, did this have to form in a direct collapse? But if we can find this within less than 1 hour of data from our SEARS program, I can only imagine what we can do with big, huge, deep spectroscopic surveys. So I think in addition to early galaxies, we're going to be learning a lot about early black holes. Okay. So SEARS is wonderful, but again, it's not a large program. Its depth is limited, but there is a much deeper survey happening in cycle 1, which we're also leading here at UT Austin, called the NGDeep survey. And we just got our first data a few weeks ago. So this is the next generation deep extragalactic exploratory, it should be public survey, not probe survey. We love our acronyms in astronomy, and I'm co-leading it with a couple of my friends and colleagues. This is our survey logo here, sort of showing the shape of the JWST mirror, and then we're sort of highlighting a spectrum of colors, both to represent the fact that we're doing spectroscopy and imaging, and also to represent the inclusive nature of our collaboration. And so NGDeep is cool for a variety of reasons, but first of all, it's actually 2 deep fields in 1. With JWST, you can use 2 instruments at a time. And so we're doing a deep imaging survey, which I'll tell you about in a second, but we're also doing a deep spectroscopy survey. And so this is actually showing an image of the Hubble Ultra Deep Field here. We are now getting a spectrum from every single galaxy that we could see in the Hubble Ultra Deep Field. We expect to get spectra for about 2,000 galaxies. And that's going to do a tremendous amount for our understanding of many things, including low-mass galaxies. And this is work being led by UT Assistant Professor Danielle Berg, who's studying the chemical enrichment and feedback loop processes in these low-mass galaxies. The other half of NGDeep is creating the first JWST ultra-deep field. And this is an image, again, we just got 2 weeks ago. Again, we'll have one online. You can download it. It will look a lot better here. But it's beautiful. And what we're looking for are, again, faint red dots. But now because we're staring at the same spot for ultimately it will be 120 hours. We actually got half of our data now. The telescope had a hiccup. So the other half we have to wait 1 year to get. But we do have half now. And it's already amazing. And we want to look for faint red dots. Okay, and we can zoom in. And there's a lot of beautiful structure. I just love this spiral galaxy there. You can see an immense amount of detail. And this is work being led by UT postdoc Jean Lung, who has spent countless hours over the past couple of weeks trying to learn how to reduce these data. There are so many new problems we're uncovering. Nobody has gone this deep before. We discovered a new problem with the data that Gene has been working on to solve, and he has solved. And so this image is beautiful enough. We'll have an even better one in a week or so. All right, so let's go back to our gallery here, and let's see what just this earliest view of NGDeep. We're actually working with what I would still call kind of the dirty version of the images. So we're being a little conservative here in our selection, but we're finding lots and lots more early distant galaxies. Slow it down to be more dramatic as we go to higher redshift. There we go. Including this amazing one here that looks like it's at about a redshift of 15.5 or 16 or so. So another way to look at how unexpected this is how high a redshift did we think we were going to go? If I go back and look at the SEARS proposal, we would be lucky if we got to redshift 11 or so. So we didn't think we'd push much beyond that, and a lot of these galaxies are from SEARS. Likewise, with NGDeep, we were sort of really targeting redshift 13 or so. And this is just like really the first glimpse of NGDeep. There's probably, I don't know, Gene, what do you think, 5 times more galaxies in this image than we found so far. So I think we're going to learn a tremendous amount more about the unexpected nature of galaxies in the early universe. But already what we have is just completely mind-blowing. And I just wanted to bring it back to where we were at with Hubble. This was in July, like July 1st of last year. And I've already become so jaded saying redshift 12, 16, 17, whatever. But it was fun to make this and just kind of blink back and forth. And this is, again, just a small glimpse of what we've got from this telescope so far. But I think we can say very definitively now that the cosmic dark ages ended quite early, very much at the early end of when we thought that might be. So to put it in different terms, you've heard this, I think, in every talk today is use the tip of the iceberg analogy. We really could only see the tip of the iceberg with JWST. But now with this fantastic new $10 billion telescope, we can zoom out and see the amount of destruction that is on my street. Put it in Austin terms for you. Still there, we'll see. I don't know what's living in it these days. So what I've showed you today covers, again, just a small amount of what we are going to be able to do with this telescope. And what's incredibly exciting about this telescope is what we're doing here in Austin. So I've told you about 2 programs. There are many other programs being led here, including Cosmos Web, we've heard about. There's a spectroscopy program being led by Assistant Professor John Chisholm. He just showed me a spectrum on his phone at the dinner last night that was incredibly exciting. In fact, 10% of the telescope time came here to UT Austin. I calculated that's about a $100 million value. If you take a $10 billion telescope, divide it by, let's say, 10 years, and then divide that by 10 again for 10%. So that's pretty good. We didn't have to pay to submit proposals, only with time. 200 of these hours belong to Cosmos Web, co-led by UT Professor Caitlin Casey, and we heard about that from Olivia Cooper earlier. And some of you may wonder, like, why would you do both? Why would you do NGDeep, this deep field, and Cosmos Web? And the answer is they're very complementary. So Cosmos Web, as we heard earlier, is about 3 times the area of the full moon. NGDeep, you can't even see it. It's a tiny little speck on that full moon, but it's going much deeper. So NGDeep is literally staring for 120 hours. Cosmos Web is building a big mosaic over a little over 200 hours. It's going much shallower. So Cosmos Web is about big, massive beasts in the early universe. NGDeep is about finding those tiny little babies, maybe 150-pound babies, but probably tiny little babies. All right, and we talked about John and his exciting spectrum. OK. So the UT advantage, why are we getting all this telescope time? And it's really people plus resources. So the people here are amazing. This is a picture of our last faculty retreat, which is a little outdated, but we're doing another one in a little over a month, so we'll have a new one. The faculty are amazing. The people are amazing. The postdocs are amazing. The graduate students are amazing. And so much of that is due to support from many folks here in the room. And then, of course, our resources, our fabulous McDonald Observatory, both the HET and also the smaller telescopes here, and the Texas Advanced Computing Center. In fact, you may think I'm an observer. What am I doing with a supercomputer? All of our JWST data reduction is done on TAC. Some of this you could not do. We actually had to apply for these. I didn't even know they existed. High memory nodes. We needed like 4 terabytes of memory to make an image. And so that's an immense resource. Not many folks have that kind of computational power at their fingertips. And of course, the GMT coming online in the next decade, which is really going to be the complementary spectroscopic follow-up tool for JWST. You can do spectroscopy with JWST, like I've showed you, and it's transformative. But the GMT, think about where we've gone from a 2.4 meter mirror to a 6.5 meter mirror. GMT is about a 25 meter mirror. Yes, it's on the ground, but it's very complementary. And so that will be truly transformative. OK, so with that, I'll summarize by just saying we've learned an amazing amount from the first year for what we hope will be a 20-year mission. And I can't even imagine what discoveries will be to come. So thank you for your attention.
Thank you, Steve.
Thanks.
All right, let's open the floor for questions, and I suggest that we begin with the in-room person, and then questions, and then we also give people who are joining on YouTube a chance as well. So, okay, and again, sort of the request is that please wait until the microphone has arrived so that everyone then can share.
Thanks for the amazing talk. Quick question, it might be outside of your specific area of expertise, but it seems to me that the telescope is collecting an astonishing amount of data, and I'm wondering what mechanism is used to transmit that data from the telescope to Earth?
Yeah, it's a great question. Technology that is not new. So the telescope stores data on a solid-state hard drive like you have in your phone. In fact, your phone probably has more data capacity than JWST. I think it can hold 64 gigabytes, about. It's not a lot. It can then downlink its data twice a day, about every 12 hours, using what's called the Deep Space Network. It's a network of 3 basically radio observatories around the Earth, or radio dishes that collect the data. But that 64 gigabyte is basically limited by the fact that the technology to launch into space can't be that year's technology, right? It's sort of set, much farther in the past. So yes, it has more capacity than Hubble, but there are always data volume limitations. In fact, this deep field survey, we had to make decisions and sacrifices to not take too much data, because data is only good if you can download it to the ground. But yeah, so it uses the Deep Space Network. An interesting story I heard also from operations project scientist Jane Rigby is about the Artemis mission that NASA launched. They did a test launch that sent an uncrewed rocket around the moon, also using the Deep Space Network. And if that launch had happened on full moon, the rocket would have been always pointed towards the moon. JWST would have been in that direction. We would have not been able to download data for several days. And it would have wiped out, they just wouldn't have taken it. They would have wiped out a couple weeks of the schedule. Fortunately, it launched around new moon, so that didn't happen. But we're worried about Artemis 2 and 3. After that, NASA's building something else that they're going to use to talk to the moon rockets.
Hi, Professor Stephen. Good to see you in person. We have collaborated over email. I've been following SEARS for a long time. So one question I had was about the recent 6 candidates galaxies by JWST, which are massive but very compact. What's your take from your perspective about that, and how much is it outside our cosmological model?
Yeah.
Because it's pretty unconventional from the predictions that have been there. So just to get your perspective.
Yeah, it's a good question. So to put everybody on the same page, there's a paper that just came out in Nature a couple days ago that claimed to have found sort of half dozen or so fairly massive galaxies at redshifts of 6 to 8 or maybe 9 in the SEARS data. This paper was actually submitted last summer before all the photometric calibration wrinkles were worked out. And so at that time, it was very exciting and unexpected. Since that time, with the updated calibration, the team has revised their estimates. The redshifts and masses have come down. They're still in tension, but it doesn't have to be a big problem. And so I'll give you 2 answers. One is that was not by our team, so we're doing our own version of that project. Graduate student Katie Turowski is working on that right now with the full SEARS data set. And the full SEARS data set is 2.5 times larger than the early one that team used. So if it's real, we should find many more. Cosmos Web should find bucket loads of these objects. And the second answer is the mass that you infer depends on something we call the initial mass function. So when we look at these galaxies, we basically only ever see the most massive stars. The most massive stars are so bright, even though there are relatively few of them in number compared to the lower mass stars, they always outshine everything. So to convert the light we see to a mass, we are assuming a distribution or a histogram of star masses. And we can measure that very well in the local universe because we can count stars and estimate their masses. At early times, we basically have no idea what it is. So we assume it's like it is today. I think we may already be seeing hints from the high abundance of early galaxies that the galaxies are brighter than they should be, and that could be because that mass function is different. It's more top-heavy. That would make them more blue. That was kind of what I was talking about earlier. That would actually cause the mass estimates to come down. And so we don't know if that's the answer, but that's an easy, plausible answer that, again, is sort of like, is cosmology broken, or are the stars a little bit different? And so you could explain it either way. I think fixing, if cosmology was broken and you had to fix it to reconcile that result without breaking any of the other well-tested observables, I think that's very challenging.
I was just wondering, do you anticipate in the future that information from gravitational waves detectors will complement or supplement or add to the information about the very early universe?
Yes, absolutely. And I will just say the first thing that came to my mind, which is one of the first, if not the first, gravitational wave events was from two merging black holes. And you can actually learn from the signal what the masses of the black holes were. And we talked earlier about sort of what the seed mass was for supermassive black holes. And we sort of thought maybe the seed masses would be, I don't know, like 2, 5, maybe 10 times the mass of the sun. The two black holes that were caught in the act of merging were like 20 to 30 times the mass of the sun. So that tells us already those exist in the early universe. So you can detect gravitational waves basically across all of cosmic history. And so both with LIGO and future more advanced gravitational wave observatories, we should be able to really get the mass function of black holes, at least of those that are merging, and that's a good representation of all the black holes.
Thank you, Professor. I just have a question for the image itself. Like, we learn a lot, like we have this red little dot as the redshift, but how about other colors means? Because they, like the picture they send into us, they are very colorful. I'm just wondering, is it actually the color of the universe, or are we actually adding some like effective, how do I interpret that color in the image?
Yeah, that's a great question. So all of the images I've shown you are actually infrared light, and our eyes don't perceive infrared light. We evolved to be sensitive to light in the visible because that's where our sun emits. So to make these images here, we basically have to colorize them. But we do it in a scientific way and not in a duplicitous way. The images I'm showing you, we've actually taken images in 7 different filters. And some are shorter wavelength infrared light, and some are longer wavelength infrared light. The shorter wavelength visible light is blue, and so we assign the short wavelength infrared light filters a blue color. And the longer wavelength visible light is red, so we make the longer wavelength infrared light red. And so it's a representation of the shape of the spectrum. But these galaxies are literally invisible. You could not see them with your eye. But we try and make the best representation of what they might look like in these images. On that PBS Nova special, which you can find online from earlier this week, there's actually a great segment in that about how graphic designers at Space Telescope Science Institute make these images.
Okay, such a great presentation. Thank you. So John Goodrich from, I think he's from the late 1700s. He was the first person to find the star binary. And they used that to make, they used glasses to make the telescope, like they stacked the images on top of each other, and they called it AGOL, AGOL, I'm not sure how to say that. But he was a deaf guy, and he was able to find this specific star. So I want to know, how can we encourage deaf children or deaf individuals to, you know, work with SEAR or work with your program? Because there was somebody doing that way back when, but they kind of, you know, labeled him as a Satanist and said he was crazy. But how can we encourage deaf individuals to get in on this work as well?
Yeah, that's a great question. So general accessibility to astronomical data for anyone is a worthwhile endeavor. There are certainly resources through NASA where they try to make various things accessible in that way. In terms of getting involved in the research or in the images in greater detail, I think coming to events like these, talking to scientists, encouraging them to come out to schools or deaf schools in the area. I know we have a huge deaf school here in Austin. So that's actually something I've been interested in and have talked to somebody at that school about before. So I'd be glad to talk with you further about that after. Let's see, there's
So mature galaxies orbit around black holes. So how long after the Big Bang did black holes form for these small galaxies that we see to accumulate the matter to be visible?
Yeah, that's a great question. And that's what's really exciting about where we're at right now is we are revising the answer to that question almost daily. So the one I showed you today that Rebecca Larson here at UT discovered, that's at a redshift of 8.7, which is about 600 million years or so after the Big Bang, and that's one. So we found one pretty early on. If we found one, there have to be many, because we've only looked at a tiny, tiny portion of the sky, and in that tiny portion of the sky, we only have a spectrum like we had for that one, for a small number. So we're already gearing up to look for more black holes, earlier black holes. And we'll see if they sort of adhere to our theories of how they form, or maybe we find too many too early, and then that's exciting, and we have to come up with new theories about how they form.
So, we're not in the center of the universe,
Nope.
and yet, we can see 13 billion years ago and 13 billion light years away in every direction that we look. What's our current understanding of how wide the universe is today?
Yeah, that's a great question that I hate, because the answer is unsatisfactory. To the best of our understanding, the universe is essentially infinite in size, which is hard to grasp. We can grasp, or at least I can grasp, our observable universe. So what we can see, imagine there's like an infinitely wide canvas. We can only see the portion around us that light has had time to travel to us. So we can only see objects that are close enough that a photon emitted 13.8 billion years ago essentially could get to us. And so that sets the size of our visible universe. But the universe, for all intents and purposes, is much, much larger than that. It's the unsatisfactory answer.
Oh, wait, sorry, on the side. There you go.
Hello. Question for you over here.
Right, thank you.
Hello. It seems like a lot of what we're learning is more about not answering questions, but coming up with new questions. What new questions are you and your team excited to come up with? I know you've alluded to a few already, but any since discovering or coming up with that proposal that have really got your team up and running?
I love that question, because I had been waiting forever for this telescope and heard so many times the things that we found with Hubble were not what it was designed to do. It wasn't until we got the first Hubble data we came up with new questions. And I'm like, I always had this thought, like, but we've learned so much. Surely we know now what the right questions are. And my imagination utterly failed me. And I will admit one thing to you. I will show you, and then I'll truly answer your question. When we come back to this plot here, I talked a lot about Maisie's galaxy. Maisie's amazing, named after my daughter, redshift of 12. It turned out it was actually not the most distant galaxy in our data. This monster over here that's going to pop up at redshift 16 is more distant. I did not find it. Where is it? It's coming. There it is. I did not find it because, remember I told you I thought we would only find redshift 11 based on our understanding. So my fancy code that searches for galaxies stopped here. I didn't look, so somebody else found it. Now, when I say, oh, go look further, we find it too, we agree, it's great. So I had a little bit of a failure of imagination, how crazy the universe would be. So what new questions are we coming up with? I think the biggest one for me is, why are these galaxies so bright? No offense to Volker, who's been theoretically predicting this for years. I never thought we would really see a huge change in galaxy spectra from high-mass stars, extremely low metallicities. I thought by the time something is big enough for us to observe it, it must be fairly mature. And I think that answer is probably wrong. I don't know. And so the best thing we can do is actually take spectra to measure the stars in these galaxies. And what we're really looking for, actually what we wrote a proposal to look for is neon, which is fun. Neon is formed in stars, actually should exist fairly early on, but there's a particular emission line from neon that you need really, really hot stars to excite and see. And so that's one question. Another question is, how ubiquitous are black holes in galaxies? We're finding them lurking in these small galaxies, and we only have the data to see it for a small number of objects. Are they truly everywhere, or are they only in some galaxies? How small do they go? Just a few of the questions I think we've come up with.
So my question is a temporal question. You mentioned at the beginning of the talk that one of the things we're interested in is, of course, how we came about. Do we already know, or is Webb adding to the knowledge of when would be the earliest age in the universe that you have enough generations of stars to develop intelligent life?
Yeah, that's a great question. In sort of a roundabout way, yes. And that's through this spectroscopy. So for example, I showed you this little blip that I said was oxygen. right? So we can use spectroscopy to understand the abundance of particular elements. And so we could look for things that we know we need to support life, right? You need, as far as we know, a rocky planet, so you need iron, magnesium. For our bodies, you need carbon, you need oxygen for our bodies, for water, other things I'm sure I'm forgetting in the moment. And while we are seeing, yes, some evidence that some galaxies are very primitive and don't have their heavy elements, we are seeing by fairly early on, at least these galaxies here in sort of the extreme end of Hubble regime, they do have a lot of heavy elements. So rocky planets potentially, maybe, could form very early. How long does it take life to evolve? Way outside my comfort zone to answer that one. I have no idea, but the pieces, at least, were in place. And in fact, I'll say one more thing. Dust that we see for very early galaxies, which are sort of conglomerations of magnesium, silicon, and carbon, we can see that actually not using JWST, using radio telescopes. And we're also seeing that in the very early universe. And in Seiji, another result he didn't talk about, we've talked about, there's a galaxy we think is at a redshift of 10.5 that looks to have a ton of dust. And so that's a sort of another angle to be excited about, that if you're forming dust, you're probably forming planets.
Over here.
Hi, I'm a science and engineering teacher at Deer Park Middle School, and I have, I'm fortunate to work with deaf kids. I'm asking for my students, what what suggestions do you have for my aspiring astrophysicists?
Yeah.
The next generation.
Yeah, I think as much as they can read things, dive into things, find what interests them. Astronomy is huge, and if they say I'm interested in astronomy, there's so much there. Figure out what interests them, and then truly dive in. I think the NASA web resources are amazing. NASA puts a lot of money into education, and so for probably any area you're interested in, you could find information on that. But please don't hesitate to come talk to me, because I have other ideas that people in the department that might have that could give you resources as well.
I think we have time for one more quick question, and then we should at some point also let Steve get some rest. And but if there's any remaining quick question, please.
A web question, or no, we do that.
Do we have any web questions?
No. Okay.
All right. So with that, then I would say really let us thank our wonderful speaker, Professor Finkelstein, one more time. And that is the conclusion of our winter meeting 2023. And then to all members of the Board of Visitors, of course, we absolutely hope to see all of you in July in West Texas. And for everyone who has joined us from the public and on YouTube, it was really great hosting you for our great lecture. UT Astronomy was really very happy to host this event. So thank you, everyone. Get home safely and all the best, and then we see you in July. Thank you.